Yes, we hear you.
All right, thank you. Okay, so what I wanted to do today, as I promised, are two things, as a matter of fact. One is to show you the distribution, as I promised, of the class. And that is on overall grades. So I have to say that I am fairly satisfied because I'm not sure I told you on the previous, so I'll repeat it. And so I apologize in case I have already talked about that. But in every class, the usually the way things go is in terms of performance. It's like we have a group of runners that all start at the same line, all right, at the same time. So the fault distribution at that moment in time is like 1. Everybody's along the same line. And then what happens over time? Usually it spreads out. And how does it spread out? It spreads out like that. So there is a bulk of runners that go together in the front, and then there is slowly a tail that develops. Okay. Now, depending, this is in fact what happens at this point in the midterm, if you like. If you have run 5 miles, you have another 5 miles to go. All right. So that is usually if you keep the same pace as for all of you, that applies to all of you, then obviously that is going to continue. However, what happens with social statistics, usually, especially with running, the first few runners are going to not only go with the same pace, most probably they're going to build it up. All right, usually towards the end, they run extremely fast. That's what happens. They have a slow pace and then keep running. And then what happens with this group, each one runs with a different velocity. And then what happens? Social statistics, not this anything specific to this class. Usually this starts moving. The peak of what we call the Gaussian distribution develops more symmetrically, this distribution, and the peak is at the center. Now, I think we can violate that if somehow you try to all keep up with the challenge, all right? Usually, in the class, I define what the maximum performance will be. So do not relax at this moment and say, okay, I'm here or I'm here. I think I can stick with that. No, I think your effort should be to move from wherever you are higher. Because if we keep this kind of distribution, it depends on you, it does not depend on me. Unless I start becoming unreasonable in what I'm giving you, right? The whole thing then is going to move lower. If I go crazy as a faculty member, I start giving you weird things, then I'm not going to change the distribution. I'm going to only change the position of the distribution. So I'm going to shift it low, but the distribution, it depends only on you. So you need to remember that. If we keep the distribution this way, then, if you remember what I said, my band for A, it was 1,200 points, assuming that the maximum was like 5,200. I consider that if we double this, because we're in the middle of the semester, there are a few homeworks. I did some kind of calculation. I think if we keep going the way we are, without any unexpected interruptions, then at the end, with the final, that we are going to be close to 5,100, which means in 5,100, the group that is going to get A is going to be in the top 1,200 points. Did I not promise that? I'm going to keep this. Which means the majority of these students, if they continue like that, will probably come out to get an A. And I don't have a problem in this class giving an A to everybody. If all of these were to squeeze and come within my own band, then I have no problem to give an A. to everybody. I don't grade on this distribution. I set my own band, and if you make it there, everybody can get it there. If you get out of this band, which you know what it is 1,200 points, then it's your decision to get there. Unfortunately, all right, if you look around in this class, the size of this class is a lot bigger than it shows here, which means, with exceptions, there are always exceptions. So there is never one case where a generalization applies to everyone, all right? So with exceptions, the majority of these students will follow even more behind. There are a lot of students who do not necessarily follow this class very closely. And that is the problem. And I worry about this, as I worry about some of you if you start feeling confident. So the distribution is your job. My craziness can move that point, which I'm not gonna go there, all right? I will always like to see a lot of the students got 200 points in the midterm, right? These are overall numbers. So my goal is to push into the A group as many students as I can, but I will do it if you help me. Meaning, you have to give me the points. I'm not gonna give you points. You give me the points with your work. All right? Give me the points and I will, and you are gonna place yourselves in the right position. So that's how it goes. So, any questions about the grade distribution? Okay, yes.
So is there, because you said that there's that whole star system where like if you have an 85,
yes.
then you get 4 points.
Yes. So that system, let me talk, thank you for reminding me. I said in the beginning they're gonna do it even in the midterm, put the stars. However, I don't, I don't worry about the students who are up here, and we'll keep going. But a student somewhere in here may find himself or herself getting a star now, but eventually losing it later. I don't wanna have to subtract points, all right? So I decided that I will give the stars for everything but the final, right before the final. So the moment we are ready to go to the final, you're gonna see all of your stars, all right, with the exception of the final, obviously, since we're not gonna have it. So what will the stars do? The stars will help us, will put, first of all, they are more for in recognition of your efforts, all right? The students who are speeding up their efforts. So they try to stay with the group here. The students will be recognized and giving the stars from 75, 85, in fact, this is the whole group we're talking about. 75, 85, 95, it benefits the students who keep up their progress. So you're gonna have those. The students who don't care about that, they're gonna start moving out of the center of the distribution. So that's what I have. I will give them at the end because I thought if I give stars and then I remove, and you know how much discussion is gonna go back and forth, people will get confused. They're gonna ask me why my grade was, my points were higher there and now they're not high, and I don't wanna have those discussions. I just, you, however, can see if you are at the 75% of any, can you see those percentages? Or you cannot? Can each one of you see your grades in percentages at all or not? Okay, if you can see your grades in percentages, that's what it says. It shows you if you are at 75% and above, between 75 and 85, you know how much you're gonna get. Between above 85 and between 85 and 95, you're gonna get the 75 plus the 85. Between 95 and above, you're gonna get all the three of them. So you can figure it out more or less what you're gonna be. But of course that applies to the whole group, all right? So it's mostly like that. And it's not so much for me to grade. I don't need that for grading. It's mostly for you to recognize your efforts. These ones do not include the stars. Any questions? Okay. Any concerns? You can tell me concerns. I'm not gonna get upset. So there is, yes. Excuse me? This distribution is what we are now, okay? It's gonna change as we move forward. What I said is that I cannot change the distribution. You can. If I get crazy, that's what I said. And I do crazy stuff. If the maximum is here, the whole distribution is gonna move lower, but the distribution by itself is not gonna change.
So what you might think is that the graph itself will
It means that usually what happens is, I need to translate it in your, if for example, you feel comfortable right now for being here and you slow down and you don't keep up with the front runners, then you're going to start moving away from the center. That's what it means. And usually these people who are here, if they have performed this group, if this group has performed, say, I don't know, I'm giving you an example, has performed at 85%, a lot of people from this group in the second semester, they're going to start going to 90%. So they will start improving for a number of things. The beginning of the semester, always things are not, you try to get to settle in the class with the instructor, with the whole system. And, you don't necessarily perform at the maximum, but when you come to the middle of the semester, that a lot of these students will start performing better. So you have to keep up with that. Any questions? Okay. There is, now next, what I wanted to show you were some pictures that I have, where I put them. Yes, I know where I can find them. And those are pictures of integrated circuits that I would like to show you, since we are talking about transmission lines. I would like them, I have them here. So I don't know how to get rid of this. Can anybody tell me how to start splitting the screen? I did it by accident, I think. Oh, okay, good, I found it. Okay. I got everything. I have a lot of pictures to show you from here. So one is this one. Okay, this one is a microprocessor. Okay, all of the lines, this is a small chip, as a matter of fact. The DES, I don't necessarily know what DES, but it's designed as a microprocessor. It's designed to do very specific things. See all of these lines. All of these lines around it, you see that they end in a ring. Usually this ring, it shows the perimetry of a hole that is metallized inside, goes through the wafer, and connects to the back side of this one. So back from this, there are similar pins here. All right, so some of the pins connect directly here, some of the pins connect from the back. There are always holes everywhere to give you an opportunity to connect wherever you want. All right, so usually this is how the chip comes. The chip comes like this and has all kinds of holes around it, as many as the inputs or outputs for DC, for all kinds. This is in fact the microprocessors, everything is DC. As many as inputs, your connections will be to other chips or could be to a DC source. all right, from all of this here. But you see how close the lines are here? They don't care about coupling. I mean, they do as long as they keep the lines far away, and you can see that if this is the line, there is here a little bit of diffraction, so you can see, you cannot see exactly how thin those lines are. But I would say the distance in between these two is about twice the thickness of each one of them. If you have two lines, two strip lines that are about twice the thickness away, then you don't have much of the fields are much more contained, you know, with from the line to the ground, as opposed to be connected to the lines. So there is a ground underneath all of those, obviously, and they place them close enough, but not too close to start having problems, all right? You remember we said if it's too close, then the charges will see each other and they will create, if you have positive charges here and positive charges here, if you bring this second line to this one much closer, then these charges are gonna force some negative charges to slow up, so they're gonna change the size of the charges, the number of, the volume, the number of charges that will come here. Okay, so they are distributed, they is dense, they try to make it as dense as possible to be able, because this is very small, but at the same time, that can be 1 millimeter, for example. But at the same time, they keep them far enough. The distance between DC lines is much smaller than the distance between lines that carry AC, which is like those cosine functions, all right? So now, what I would like to show you next is one case. Look at this. What do you see here which is of interest? You see, I would say if I am to look at that, I would say I see a number of lines, but a number of them. But I will correct, and that is in fact what people are doing in modern circuit design. In the old circuit design, the older the design, the more of this you're gonna see. There is more restriction on how to lay out your circuits because we had only one side fabrication. So it was a metal on one side everywhere. And then we had all of the other lines to be deposited on the other side. So they would put wafers that had already metal on one side, and they would only do the evaporation of the metal on the other. And they do different shapes. Now they do evaporation on both sides because they have the instrumentation is available. So now you can do very interesting and very unique kind of designs as long as you're not constrained by geometry, you're not constrained by the wafer, you're constrained only by the physical laws that apply, all right? So here, for example, look at these lines, how close they are. They're so close that even when you take it from this, you cannot even see. These are digital lines, okay? And then mixed up with them, you will see some lines like that. These are AC lines. As a matter of fact, these lines do not have any ground at the back because one is a line that brings the current like this. The current comes around, goes like that. And as a matter of fact, if this is a hole, so the current may part of it may be connected with something in here. The other possibility that we can have is that if there is a hole here, and I'm not exactly sure because I cannot tell from here, then these lines will connect through these. So practically you have two coupled lines or street lines, you can call them. And then this connects to another node at the end. Right? I don't know. If it's not connecting to another load, then that is a small inductance that serves as the load, and the lines, what they bring is a current that flows one direction here, the other direction there. So practically it brings along this line, in between the lines, it brings an AC wave, all right, that stays there. And you will see, we'll call that a standing wave in a week or so. And these are See how far they are compared to this, the same thing here. 3 lines here. One is the ground, 2 lines are the signal lines. This is called the coplanar waveguide. This is called the strip line. So I'm telling you that this nowadays people are using a lot of creative ways to do the same thing. All of these lines carry AC very nicely because they're designed so. And these two. Now, what are those? Some of those are vias, we can see from there. Some of those are small inductors to measure. Now, what you see here, which is interesting, you see this line. You can argue this, I don't know about that, but definitely this line very much approaching this brown thing. What do you think this brown thing is on the basis of what you've seen so far? If you just see a wire like this, what do you think it is? If it carries a current, what is it going to be? A loop, what is it? Inductor. Now here, that does not directly connect with anything, but it goes very close to a line that carries an AC current. So, because there is much more, the AC waves are reaching more out, there is what we call a, because of proximity, there is an induced current here. All right, so here there is a current, it's not as strong as here, but because of proximity, it induces a current here, all right, which starts running like that. Okay, so you have an inductor. If there is a ground underneath it, what else do you have? If you have a wire, a flat wire, but it's on from a distance from a ground, in addition to the inductance, what will this wire have? These two. When we have 2 conductors like this, what happens? Capacitance. So this has an inductance because the current flows like that. This is an AC current. And because there is a ground underneath it, it has a capacitance because it excites both the magnetic field because of that, and it excites an electric field because of the other ground underneath. So this is what kind of a circuit? LC. What does an LC circuit do?
Stores electrical.
And electric, and then it changes to magnetic, and then from magnetic to electric. How do we call those circuits that have an L and C and they keep changing the electric energy to magnetic forever? Resonate. Well, how else it is called? Oscillate. Because, you know, you have the energy oscillating from one electric to magnetic, magnetic to electric. What is this called? A loop resonator or a loop oscillator. All right, so practically by doing this, what have you done to your circuit? You have introduced an RC circuit. That you see it symbolically as an RC, but this is geometrically calculus. All right, so you have one here for high frequencies. I don't know what the reasons for this circuit is. I cannot tell more than that, but I wanted to show, first of all, the 2 types of lines, the distances that they put between lines in their AC, and how close the DC lines are. And now that's one loop resonator and one single loop oscillator. Okay, as you can call it. All right, so now, just to give you a sense of how things look in real life. But now going to the things that we would like to learn. So number 1, these are 2 strips. You saw them like being on the same surface like that, but here we have them separate. Even if you have them on the same surface, they will do the same thing. from what they would normally do if they are separate surfaces. You just need the dielectric to keep them in place, all right? There is no other reason for the dielectric but to keep the conductors at the same distance from each other. If you print them on top of the dielectric, you can print them to be in the same distance. If you print them on each side of the dielectric, you can print them to stay in the same distance, right? So that's what's happening. Now, what I said before is, if there is a current that flows, that is an AC, like a cosine of omega t minus beta x, for example, then this is going to create a electric field like that, approximately. And I will explain why I say approximately. A magnetic field which is well confined here. And the one thing that you want to see, you will see from here, is that both the electric and magnetic fields are perpendicular to the direction of the current. And because they are transverse, we call them a transverse electric magnetic wave. This is the name. We never say the whole thing, we call it a TEM. A pure TM wave is what you're going to have. Two strips are like this, but in free space. What does it mean, quasi? Quasi means the following. We are going to come to this a little more later. It means that by the moment that I introduce the dielectric, and of course, the moment we have two finite strip conductors, finite in width, and of course length and something, but also being separated by a particular distance. The presence of the dielectric introduces, and the finite dimensions and so forth, introduce some parasitic effects. I'll talk to you about what that is in a moment. But because of the parasitic effects, complex structures like this, that they have this kind of dielectric, instead of having only an electric field like that, going perpendicular from the to the surface of the conductor, and the horizontal magnetic field, they also have some small additional components in the field that go along this direction, which we don't want to have. So if these components, extra components, are very, very small, then we ignore them, and then we call this wave a quasi-TM. All right, so that I'm using that because I'm going to use the terminology. So I want you to know what the terminology is. Okay, so quasi-TM, whenever you see it, that's what it means. So now we are going to this kind of structure. That's yet another type of a transmission line. Always in transmission lines, you have two conductors. Remember that? And maybe three if it's a coplanar waveguide. You cannot have a transmission line with one conductor. You remember that? I may ask you a question about you remember? Don't show me one line and say this is a transmission line. Okay. Two or more. And not just more just because, it has to be a reason for it. But at least two this way. Okay? One is the ground, and the other is the conductor. All right, one carries the current that goes from the source towards the load, and the other is the return. Okay, only the electric, because obviously we have separated. If I were to take this problem and introduce a small h, introduce a much wider w, and so forth, and I use one of these HFSS, which means the accurate way to find the distribution of the electric field. The distribution of the electric field is not going to be the one that I saw simplistically, but at the edges, it's going to have these curved electric field lines. Why is that? Because one thing that we have neglected, just to make things simpler in the past, is that when you have a metal that terminates somewhere, what did we say? Yes, if you have another metal very close to it, so the charges of this metal, the upper, and the charges of the lower metal will start facing each other, positive and negative, all right? So they will come as much as they can at the center. positive here, negative there, according to that, if it's positive or that. And then there will be some charges that like the corners. You remember we said that? We said if the charges are, if here we did not have this conductor, and we had just a strip, and on this strip we would put just charges, and most of the charges will come to the edges if they don't have anything else. I mean, the only thing is going to put some charges here is like the repulsive force between the same charges, the same positive charges. Otherwise, they love the edges. Okay? So, of course, we have some of this here, and those they create that kind of thing. When we use this assumption that you see down here, when from here we go down there, if we don't take if we don't make any adaptations in the geometry, we're going to lose all of the energy that is included there at the edges. And in reality, depending on your operating frequency, this energy might not be so small to neglect it. Might not be negligible. Maybe it's big enough so that it needs to be included. How do we then therefore do that? What do we do to make sure that we include this energy? We develop an equivalent circuit. And in the process of doing that, as a matter of fact, we also remove the dielectric. In fact, we remove this excess dielectric. What we do, look at this at the simplifications. We go from the microstrip. We try to neglect these edge effects. We call them edge effects. And says here, we ignore the field at the edges. And then in addition to that, we try to shrink the lower conductor to make the lower conductor the same with the upper conductor, and also remove the dielectric, which is beyond the edges of the conductors. Now, for this problem, which is something that we have seen and we know how to solve, to be equivalent to this one, to the original one, we have to make some changes in the geometry. And there are two specific changes we make in the geometry. We do not touch the thickness. The thickness remains what it is, but we change W to what we call W effective. So we make it a little larger. All right, then I will show you how much larger it gets. And we make the dielectric a little denser, meaning higher relative dielectric constant. So we create a new structure that is simpler. However, you can argue in terms of the energy, electric and magnetic, that is stored in this structure is equivalent to the electric and magnetic energy of this one. And how do we find the formulas that help us do that? We are not finding them here, obviously. They are semi-empirical formulas. Do you know what we mean by semi-empirical?
You can get most of the way from just equations.
Yes, and then the rest from experiments. So you have some kind of equations. You cannot solve all of the equations and make them be simple. And then you can find some coefficients through experiments. So you see, you make an experiment you make an experiment with this, you make an experiment with a microstrip, and then you try to find out what you need to change to make their characteristics. Very similar. Okay, so we found we have to increase the width by a delta W. We have to increase epsilon effective by this number, where alpha and B, where A and B are two parameters that we have defined empirically. And this is called the parallel plate waveguide model. It's not a real waveguide. The real thing is a microstrip. This is real. This is real. The other one is a model, and we develop it like this. And these numbers are extremely important when we are gonna try to then represent that symbolically, okay? Any questions before I continue? Okay, so now we have 10 more minutes. Good. Right. Let's assume now that we've done all of this. Okay, we've done all of this. And now I want to take one more step. I'm not very happy. I mean, I'm very happy that I came here, but I'm not done. What I would like to do is to make it even simpler, because this is equivalent to microstring, but still a three-dimensional structure. All right. In fact, this is just a cross section. In reality, this one will go like this. Okay. So it's three-dimensional structure. I don't want to work with 3D structures. I want to work with symbolic representations. I want to have RLC, because that's what I know well. I don't want these things, because then I have to go to full-scale models. I mean, I have to go to HFSS, ADS, and so on. All right. So what do I do next? Yes.
What is E sub r again?
E sub r is the relative dielectric constant. So for example, if the material here for if the yellow material, let me just do this here. So when you read it next, remember, if this yellow material is duroid, epsilon sub r will be around 2.4 to 2.7. If it is glass or quartz, as we call it, epsilon sub r is 4. If it is silicon oxide, epsilon sub r is like 2 maybe 3 to 2.8, depending on how you make it. If it's silicon, epsilon sub r will be 11.7. If it's gallium arsenide, epsilon sub r will be 12.3. If it's alumina, or alumina, not aluminum, alumina, which is kind of a ceramic, epsilon sub r will be 10. Okay, that's what this is relative. And so an epsilon, therefore, for all of these will be epsilon sub r times epsilon naught. Okay, and epsilon is the dielectric constant. Okay, now let's assume that I take, first of all, this line and now I have two conductors. Of course, much wider, right? They are not as narrow. I just, again, H will always be, let me write here H. H has always needs to be much less than W. This is W effective, if you remember. And this is epsilon effective. All right. And then here, let me see. So epsilon effective is going to be, so practically epsilon here will be epsilon effective times epsilon naught. All right. So this is the material that we have here. Now, what I want to do is make sure that I change these and those extend like that. All right. I want to make sure that I can change this first of all. Now I'm going through more transformation. I want to replace those with a thin wire for the top and another thin wire underneath it. And I want to assume, so what I do with this, while I keep the length the same, I have, by going from what they are here to the thin wires, so here, let's assume that this was that. By going to thin wires, I have already eliminated the geometry of the cross section. I have squeezed my cross section. I have just taken literally 2 wires and say, I would like these 2 wires to represent this. What do I have to do? I'm asking. If I can find, what do I have to do to find 2 wires to represent this? And that question is a little more complex. Why is that? Because when you have, and in fact, to be able to do that, I'm going to write it here, explain to you. At the end, what matters is the current that I let flow here. It's going to be, of course, a current distribution, because it's going to, the charges are distributed, and therefore, when the charges run, the current is going to be distributed. It's going to be the current distribution, and the current here is going to be the total current. Let's assume that the distribution, let's assume that this distribution here of the current, let me show it with, the current distribution is this, all right? And then it flows like that. And the return current, it is the opposite way, goes like this, and it distributes like that. Okay, first of all, to be able to use this model to represent this, I need to have a current that flows here, which is the total current that flows on the upper strip. All right, so practically, the current that it will flow here is going to be I, all right? And therefore, which is where I is going to be the integral, say from 0 to W effective, of this current distribution. And let's assume that this is, if this is, and this is Z, this is X, this is Y, and this is Z. So it's going to be I of X dx. So that's your total current. So I integrate all of this current, and I give this as the current that flows here, which means instead of having a density, which is a function of X, now I have a total current, and X does not exist in there. So that's number 1. Number 2, I want to eliminate the sense of this thickness. I want to make sure that I don't have to worry about this thickness. And therefore, here is just 2 wires very close to each other, where the thickness does not matter. All right? But I want to keep sure that whatever voltage I have applied between these 2 plates, that voltage remains. So practically, I want to, if this is the voltage here, and then let's put V, that voltage that applies between these 2 plates. And the voltage is not going to vary with X, because the voltage is the difference between the potentials of the 2 plates, and the potential on a metal is the same everywhere on the metal. Remember that? Do you remember this? Remember this, that the potential of a conductor has the same value everywhere on the conductor. So this conductor has one potential, this conductor has another potential. The difference between these 2 potentials gives you the voltage. So now I'm going to say that I want this voltage here between these 2 to be V. So practically, if I can find this V and I can find this I, the total, not the density. Then I want B and I to be preserved in my new model. When my B and I are preserved, then practically, holistically, this gives me the same result with this, even if I do not know, I cannot find in this symbolic representation of this, what's happening at every point inside. I lose the capacity to anymore calculate all of the fields here. Because now I got rid of the fields and I kept only the voltage and the current. And if I do that, then practically any transmission line can be represented by two thick lines that look like wires, but they're not wires. So for example, if I do this, I don't know, does not help me here. No. Okay, got this. If I do this and then I got here, then see what I'm gonna do. I'm gonna put a node here. I'm gonna put another node. So now I have two thick wires, like these two in here. They have only one dimension, and the dimension of this is only Z. All right? So practically, this is my Z dimension. Z. Let's assume here is 0. We can put the 0 wherever. For a moment, I'll put it there. And then let's assume that I'm going to connect this line, which has a length L. L. I then can connect it to a voltage source here, V, and to a load. Let's assume that the load is a resistor at the end of it. So what did I do in the process? I took a three-dimensional structure here, like this one. And then I went through these transformations and I brought it into this form. It has a length, obviously, still 3D. And then I took this transformation, this had a length there, and then I went here. And then what I did, I just X'd all of the dimensions with the exception of the length. And I have been able to now represent symbolically this line by two thick lines. There will always be thick lines. You have to remember that. So, and why is that the case? Because then we remember that each of these lines is not independent. They work together only. And they have a length. It's not like the other circuits. You know, when you do here an RLC, when you do an RLC circuit, say R, L, and C. Other than the electric connections, is there any physical dimension in this? No, there are no physical dimensions here. But here, in this, there are physical dimensions. So if you are at point A, usually the points are going together. So we call this port, the input port, AA prime. We call this the output port, BB prime. Input port for the transmission line, output port here. If you are at AA prime and then you move to C prime, your current then is going to be different and your voltage will be different. But in what way? It will not be arbitrarily different because the current change like this and the voltages things like this. Of course, if you have a length of the line, you're gonna be at any point here. If you are at the beginning, you can be here. If you are in the middle, you can be here. If you are at the end, you can be someplace else. All right. And what we will see is that the voltage and the current, they are out of phase. So in any case, we are gonna start next time on Friday with this model. It has only one dimension, all right? There are no dimensions here, there are no dimensions there, only here. And we are gonna then define the properties, the propagation properties of the waves in this line on the basis of the previous geometries. And that's how far we're gonna go. And then you forget about the previous geometries. We only work with a line like this. All right? All of those are introductions. So on Friday, we're gonna be able to start thinking of this along.